If Canada did not have the F-35, do you think that American planes would more often be in Canada?
That changes our, defense capability, and as such, we have to figure out how we're going to replace that.
Can we maintain our sovereign control of airspace without F-35s?
I would offer that Canadian presence in NORAD absolutely reduces the risk and increases Canada's autonomy and ability to defend itself.
Modern air combat is often described as a contest of technology, stealth coatings, sensor fusion, and digital dominance woven together into a seamless web of data. In that conversation, one aircraft is usually presented as the benchmark against which everything else is measured. Yet beneath the surface of that narrative sits a quieter debate that defense planners rarely frame in public. It is not about who sees farther on radar or who carries the newest missile. It is about what happens when the network fractures, when runways burn, and when the system that holds everything together begins to fail. That is where a different kind of advantage starts to matter. In nearly every public discussion about fifth-generation fighters, the F-35 is described as the future made real. Stealth shaping reduces radar cross-section to a fraction of older aircraft. It's AN/APG-81. AE/SA radar scans vast volumes of airspace while remaining difficult to detect. The distributed aperture system gives pilots spherical awareness, feeding imagery directly into the helmet. Data links connect each jet into a larger combat cloud, turning individual aircraft into nodes in a shared intelligence grid. In exercises and simulations, that integration allows F-35 formations to identify, track, and engage targets long before opponents even realize they have been detected. That dominance, however, is built on a specific architecture. Every F-35 typically operates from a major airbase with long reinforced runways often exceeding 8,000 to 10,000 feet, or roughly 2,500 to 3,000 meters. Those bases are protected by layered air defenses, surveillance radar, hardened shelters, and extensive security perimeters. The aircraft depends on secure satellite communications for navigation updates, mission data files, and coordination with allied assets. Maintenance is supported by a vast global supply chain, with components manufactured across the United States and partner nations, all feeding into a centralized logistics structure. Software updates and mission system refinements are tightly controlled through U.S. managed channels, ensuring that performance remains synchronized across the fleet. None of that is accidental. The F-35 was designed to operate inside a highly organized coalition framework, where allied forces share intelligence, pool resources, and maintain constant connectivity. Under those conditions, it excels. Its low observable design allows it to penetrate defended airspace. Its sensor fusion reduces pilot workload while increasing situational awareness. Its ability to cue other platforms, from surface ships to ground batteries, multiplies the effectiveness of an entire joint force. In a coordinated campaign where air superiority is established early and infrastructure remains intact, few aircraft can match its combined capabilities. Yet that structure assumes continuity. It assumes that runways remain usable, that satellites remain functional, that data links remain secure, and that spare parts continue to flow. It assumes that the command architecture remains coherent. Modern warfare increasingly challenges those assumptions. Hypersonic missiles, precision cruise strikes, cyber attacks, and anti-satellite weapons are no longer theoretical concepts discussed in think tanks. They are active areas of development for multiple powers. In the opening hours of a major conflict, air bases would rank among the highest priority targets. Fuel depots, ammunition storage, radar arrays, and runways could be struck repeatedly to deny sustained operations. Against that backdrop stands the Saab JAS-39 Gripen, an aircraft born from a different strategic mindset. Sweden, throughout the Cold War, prepared for the possibility of invasion without the guarantee of immediate Allied reinforcement. Its planners concluded that fixed infrastructure would be vulnerable from the first strike. Large air bases concentrated resources and presented obvious targets. If those were destroyed, the Air Force could be grounded within hours. Survival required dispersion. The Gripen was therefore engineered around the concept of decentralized operations. It can take off and land on short stretches of roadway measuring approximately 800 meters or about 2,600 feet, far shorter than what many advanced fighters require. Sweden developed a system of dispersed basing known as BAS 90, where aircraft could operate from hidden highway strips carved into forests, with support vehicles positioned nearby under camouflage. After landing, a small ground crew, often cited as 6 personnel with minimal equipment, can refuel and rearm the aircraft in under 10 minutes. That rapid turnaround reduces exposure time on the ground and allows repeated sorties without dependence on expansive facilities. Maintenance philosophy also reflects this approach. The Gripen was designed for ease of access, with modular components and built-in diagnostics intended to minimize specialized tooling. While any modern fighter requires skilled technicians, the Swedish concept emphasized keeping logistical footprints light enough to function even when supply chains are strained. The aircraft's operating cost per flight hour is widely reported at around $7,000 to $8,000, compared to figures for the F-35 that have ranged between $35,000 and $47,000 depending on variant and accounting method. Those numbers influence not only peacetime budgets, but wartime endurance. Cost alone does not determine combat effectiveness, yet it shapes sustainability. An air campaign rarely ends in a week. If sortie generation slows because maintenance hours accumulate faster than parts arrive, operational tempo declines. The F-35's advanced systems require careful upkeep, climate-controlled facilities, and secure data management infrastructure. Its autonomic logistics information system, later replaced by the operational data integrated network, that integration improves oversight, but increases reliance on connectivity. Gripen's philosophy accepts that connectivity may degrade. It can integrate with NATO data links and advanced sensors, yet it was built with the expectation that communications might be disrupted. Pilots train for operations with limited external input. Aircraft disperse, relocate, and reappear from unexpected locations. Destroying one strip does not eliminate the fleet, because there may be dozens of alternative sites across a national road network. An adversary attempting suppression faces a moving target set rather than a fixed cluster of installations. From a strategist's perspective, this difference alters planning. Striking 3 or 4 large air bases with precision weapons could neutralize a concentrated fleet. Identifying and destroying dozens of temporary road bases scattered across forests and rural terrain demands persistent surveillance and significant resources. Each Gripen on a highway strip represents a smaller but harder to locate problem. Mobility complicates targeting cycles and forces an opponent to stretch reconnaissance assets thin. Stealth remains a powerful attribute, but it is not invulnerable to technological evolution. Advances in low-frequency radar, multi-static sensor arrays, infrared search and track systems, and data fusion across distributed networks aim to reduce the advantages of low observable aircraft. No public system guarantees detection of every stealth platform at operational ranges, yet the trend suggests that signature reduction alone cannot be treated as permanent immunity. If detection ranges shrink, the aircraft still requires somewhere to land, refuel, and reload. Mobility, by contrast, cannot be electronically jammed or algorithmically bypassed in the same way. A runway carved from a forest road does not emit a signal that can be targeted by cyber attack. A dispersed unit relocating after each sortie denies the predictability that precision weapons rely upon. Even if radar identifies a Gripen in flight, preventing it from operating requires locating its next landing site, striking it before departure, and repeating that process across multiple locations. The contrast extends beyond engineering into politics. Purchasing the F-35 entails entry into a tightly managed international consortium. Software updates, mission data, file programming, and certain weapons integrations involve coordination with the United States and Lockheed Martin. That framework ensures interoperability among allies and maintains security over sensitive technologies. It also means that key elements of capability remain linked to U.S. oversight. Sweden structured the Gripen program differently. nations operating the aircraft retain significant control over software modifications and weapons integration. Brazil, for example, participates in local assembly and development of the Gripen E variant. Operators can integrate a range of munitions from European Meteor beyond visual range missiles to other compatible systems, without the same degree of external gatekeeping associated with the F-35 program. For smaller states seeking autonomy in defense policy, that flexibility carries weight. None of this suggests that one aircraft universally surpasses the other. In contested airspace during the opening phase of a high-intensity conflict, the F-35's ability to collect, process, and share data across a coalition remains formidable. Its stealth profile, sensor fusion, and electronic warfare suite create options that legacy fighters struggle to match. However, the Gripen was not built to win a technological showcase. It was built to endure disruption. Consider a prolonged scenario in which missile strikes crater, primary runways, cyber operations interfere with logistics databases, and satellite networks experience intermittent outages. Aircraft requiring extensive infrastructure may face delays returning to service. Even temporary pauses in spare parts flow can accumulate into significant readiness gaps. In contrast, a fleet designed to operate from improvised sites with lean support crews may continue generating sorties at a steady rhythm, even if each individual platform lacks the same degree of low observable shaping. Turnaround time illustrates the divergence. Reports frequently cite the Gripen's ability to land, refuel, rearm, and depart again within 10 minutes under field conditions. The F-35's more complex maintenance cycles and stealth coding care procedures extend ground time, often measured in hours depending on mission profile and required inspections. Over days and weeks, that difference affects sortie count. In a war of attrition, cumulative flight hours translate into presence. For nations evaluating future air power, the decision reflects anticipated threat environments. Those expecting coalition operations with robust infrastructure and assured connectivity may prioritize the F-35 sensor and stealth advantages.